Okay, so this is lecture 3, analyzing the latent rad image. We'll just get started. So we're going to talk a lot about what affects resolution towards the end of the lecture, but at the beginning, we're going to talk about all of the different parameters that you'll have to know in terms of whether the exposure increases to the image receptor or not, depending on whether you change different parameters like SID, OID, user grid, etc. I hope this lecture will serve as a good review from what we've done last year and going forward, because unlike other classes, you're still subject to the materials that you've learned in the past, a mere 6 months ago, really. So a lot of these are what goes up, what goes down. Also, keep in mind that if the arrow is extra big and fat, then sort of it's an exponential property. So for example, here it's not going to be, it's just that MA, milliamperage, right, directly affects and is in direct proportion to the exposure received to the image receptor and to the patient for that matter. But we're looking at the IR being image receptor. So milliamperage, what happens when we increase that? The filament will burn hotter, not longer, because that's time. This is just hotter, and thermionically produce more electrons, which will ultimately turn into more photons, and you get the idea, more photons equals more exposure. Up we go. Guys want to take this one? If the time increases, what happens to the exposure? Increases, same thing, right? Except now, the MA was determined, so our filament is a certain temperature, but now how long do we keep it on, essentially, and continually increase thermionic emission, and again, more photons over that period of time will lead to higher exposure received by the patient and the image receptor. So mass, we should know this, it's a combination of MA and time, so naturally increasing total mass is going to increase exposure and dose to the patient. Certainly exposure to the image receptor. How about kV? Increase kV, what happens to exposure? Up or down? Up, right? There's a page in the book that kind of shows you an example of 2 different kV levels, and you can see that more photoelectric effects occur. Photoelectric characteristic effects occur when you increase your kV. But that's a big, big up, right? Because think about it, just an increase in 15% doesn't mean that your exposure goes up 15%, right? The rule of thumb is that it will increase 30 to 50%, almost double when your kV goes up just a mere 15%. That's why much larger arrow than what we had for MA, time and mass. It even takes its time going up. Okay, generator. So generator says that if we have a stronger, more efficient generator, like a high frequency versus a single generator like 3-pulse or 6-pulse, that it's going to give us a more efficient beam and generally a higher beam, right? So if you set 85 kV with a high frequency generator, you're going to get close to 85 kV photons, right? Which will lead to more exposure to the plate, because thus, when you think about it, stronger photons are more likely to be in the remnant beam than get stuck in you and make it to the image receptor. So it's up or down, depending on whether your generator is getting more or less efficient. Any questions on generator? Again, just like last semester, I told you I wasn't going to go terribly into generator in this course, except for how it changes the exposure to the plate. Okay, so in clinical application, using a filtration does not affect exposure to the IR. So be careful with this one, right? It certainly affects exposure to the patient. That's why we use it, right? Because the filter captures the what wavelength photons? The longer ones. I mean, at some point, where does short become long? But in general, the longer ones, the weaker ones that would get stuck in the patient never make it to the image receptor. That's why if you read this, I try to clarify that in here and hope that you understand. We're talking about the exposure to the imaging receptor, right? It wouldn't change whether you take the filtration out or not, because that would only change the exposure to the patient. You guys on the same page with me? Okay. So there really should be no effect on the exposure to the image receptor. Now, a compensating filter is different, right? The compensating filter, its main purpose, anyone use that in clinic, compensating filters yet? Like for a foot or for spine work? Like anyone see full-length spine? Anyone else? Right? When they use a full-length spine, like one big, long 3-foot cassette, right? There has to be a filter built either into the cassette or like a wedge that's placed on the actual end of the tube in order to reduce the radiation going to the top portion, thinner part of the spine, versus the thicker part of the spine should be the thinner part of the wedge to allow more radiation through. I hope I said that all right because I don't want to edit this. There'll be no editing. Okay, so in terms of filtration, again, a compensating filter may change the exposure. It probably will compared to if you didn't have one, right? If you're using a wedge type compensating filter, some portion of that beam is going to be eliminated and never make it to the remnant beam. So a compensating filter will definitely change the exposure and it would reduce it because at some point it's blocking some of the radiation and allowing other parts to go through. But the filter that is in the tube, that one that adds up to 2.5 millimeters of aluminum equivalent, that number that should be embedded into your head, that filter in the tube should not affect the radiation felt by the image receptor. Good, good, good. Okay. Sometimes I think to myself, I understand. But you guys need to understand. Okay, so variables affecting exposure image receptor. When it comes to field size, in other words, collimation, when the field size is increased, which basically says that you're not collimating, right? It's the opposite of collimating. When the field size gets bigger, you're including all that scatter, you're irradiating more, right? You're not cutting off any of the beam. So the exposure to the image receptor is going to increase, and to the patient. I might as well add a and or not and to the patient for some of these. And it's not always the same, although it's the same for most of them. Not filtration, no. Okay, part thickness. Well, if the part thickness gets bigger, you're going to have what happen? What happens to the beam? You're going to get more absorption. And this is the whole rationale for why we increase our exposure when we go from, I don't know, a stenic patient to a, what is it, hypo? Hyper. Hypo is low. I'm not editing. Okay. So in this case, in this example, right, when the part thickness goes up, and this is a big, big arrow, exposure goes way, way down because what would we need to change? What's our rule? 2 inches, 4 kV for every 2 inches is the adjustment. Well, what's a 4 cm? 4 cm, I mean, right? So remember, and that's talking about changing your kV. kV is an exponential parameter. So you really need to increase your exposure when patient size or the object gets bigger. Variables affecting exposure, like the patient condition. So this is very similar to the object size. So patient condition, pathology, there's a big up or down on this because, for example, if you have osteoporosis, you don't need as much exposure. And if you have, I don't know, ascites, a buildup of fluid, then you're going to need more exposure. So this depends on the pathology in terms of whether your exposure goes up or down. No questions, right? This is pretty obvious, I would hope. Okay. Honestly, in clinic, you're probably not changing your exposure very often from what that sort of technique that the technologist gives you based on what you see on a requisition. It's very often that, very unoften, I should say, that you actually make a change to your technique based on what the request says. So variables, and most of that is because of digital imaging, right? Which fixes it for us, right? So the only time you might have an issue in digital imaging is if you would have needed much more exposure, right? Because then you'll get noise because it can't compensate. But for example, this is not particularly good, but if the patient, let's use the example before, has osteoporosis, which would require a decrease in the radiation, let's say you don't do anything, just shoot it like any other image, or that patient data wasn't even there at the time, it'll fix it, right? Because digital imaging does good with overexposure, not so good with underexposure. Underexposure leads to noise and a grainy image. So scatter, right? Scatter is bad for exposure. And this one's kind of interesting because we're not really breaking down scatter into photoelectric or Compton, but in this case, it's which one? Is the IR going to get any photoelectric scatter? That's the scatter that gets stuck in the patient, right? I feel a test question. I should just stop and write it because there's a distinction here, right? It doesn't say which scatter, but you should know that it's all Compton, because the only thing that the image receptor can receive is Compton, right? Everything else gets stuck in the patient. I mean, you could say that the Compton never makes it to the cassette and hits the wall. That's possible also, but it's definitely not going to be photoelectric, right? Major occupational dose or dose to mom or dad or whoever might be holding a patient, which, you know, I don't want to go on a tangent, but this shouldn't happen too often. Their dose is going to be directly from Compton scattering. Well, I shouldn't even say that. Most of it, right? Unless they actually have their hand on the image receptor or in the primary beam. I've seen that actually often enough. Yeah. So, you know, baby comes in for a hand and mommy is like, well, the first thing I do is tell them to hold the hand, and inevitably they go like this. Well, so that's not going to work, right? But even if they're holding, so I'll tell them at least, you know, try to hold down near the wrist a little bit. But if their fingers or anything shows up in the image, that wouldn't be scatter, right? That would be, you know, remnant beam to them, which is bad. That looks horrible. Pound cropping. No, don't do that. Do you know there's been instances where that has happened and the radiologist has picked up something on the person who's not the patient? Yeah. So one reason not to crop is you're making a medical decision to get rid of anatomy that you don't think is worthwhile, right? And if down the line it's recognized that something was there, then you can get in trouble for that. Now, you might say, what's the difference, right? If I would have collimated, I would have gotten rid of that anatomy anyway, maybe. But that's different. Once the image is done, it's done. Now you're deciding to take image information and get rid of some of it. So there is a distinction between collimating and cropping that I don't think a lot of people understand. Yeah, so cropping, I'm anti-cropping. I know. Okay, so grids. How do they affect exposure to the image receptor? Decrease. And the main reason for this is a lot of the good photons that would make it through get absorbed by the materials that make up the grid, like the little lead lines or aluminum lines. So our exposure goes down. Usually it goes down so much that we have to compensate, which is why we learned last semester that when you have a grid, you have to increase approximately 4 times. The other textbook that I used to use once upon a time had separate intervals of increasing depending on what your grid ratio is. And I kind of liked it. I might bring it back, right? Because technically, when you go to a 10 to 12 grid versus 10 to 1 grid versus a 16 to 1 grid, that's a big jump. It shouldn't be 4 times the radiation for either of them. Just, flip a coin, right? It should be maybe 4 times for the 16 to 1 and maybe 3.5 or 3.25 for the 10 to 1. See, that's the reason. It's close. So they just said, let's go ahead and just make it 4. At least that's how your textbook approached it. Honestly, I hope I'm not doing you disservice. If you get a question that's very specific on the registry, I don't know. Blame the book. But I hope you don't. I don't really know. I'm not really allowed to ask either. And the content specs are not really clear enough to it talks about grid ratio, but okay, let's keep going. Variables affecting exposure, anode heel effect. It's almost not applicable that much because it's always there. Although it's more evident the more you increase your field size, right, over a distance. So you're going to have more anode heel on a tib fib than you're going to have on the 3rd digit of your hand, right? But essentially the rule is still true. There's more radiation on the cathode side, and that's because when the photons are created, they're coming down, but before they actually escape the anode, they get caught on the heel part of the anode and are reabsorbed and never make it out. That doesn't happen as much on sort of the bevel tip. We're good on anode heel, I hope. The rule of thumb, though, for the registry and in general, it is still true that the thicker portion of the body should be towards the cathode side of the tube, right? So that's the way you should be placing your patients. So how's SID affect the exposure? So again, you can see it does so in a big way. And based on the quiz we just had, it's based on the inverse square law, right? So, when you double the SID, right, your radiation doesn't just half, it goes down to 1/4 of the amount you started with, right? So that's why I have the big fat arrow. So when you're doing those portables and I tell you that SID is your friend because it helps reduce the minification and your better chance of getting those costophrenic angles, for example. And I just saw it when I went to Woodhull on Friday. One of the students went to do a portable. I tagged along and I saw them, basically adjust so that patient was kind of over here in the bed and they moved the machine kind of right next to the bed or the stretcher and then just turned the tube. And then when they went up, they were only about, 45. And sometimes that's okay if you don't have room, but it's in the emergency room. You have no wall behind you. I mean, maybe the nurse's desk is kind of behind you a little after a while, but so I told him this is for your own good, actually. Less chance of, provided the patient can sit up, right? If the patient can't sit up nice and high, then it's hard to do. Right? But you should get as much distance as you can. So the key point that I'm talking about here is what do you need to do to your technique? You need to increase your exposure, right? How much, depends. Do you whip out your pen and do the inverse square law? I suppose you could, or you can kind of use that sort of rule of thumb, and guesstimate. Usually people would just go up, 1 or 2 steps in mass on the console of the portable machine.
Have a maximum amount of distance as possible.
Well, be careful about maximum, because if you go to 100 SID, right, and you could adjust your technique, but then the images would get minimized and it might look like pathology. So you don't want to go beyond 72, right? And you really should annotate or note the image. Are you guys are looking at me like in clinic they went to like 118? No, something else. 10 what? 10 SID? That's radiation therapy. What do you mean 10 SID? That's no good. You mean they were like right here? See, that's so in their example that they were really close. Is that because they couldn't get the room? They just were lazy. See, but the problem there is, I don't know if the expression is that's going to bite you in the butt, right? If you end up having to repeat that exam because you cut something, was at the end of the shift and they were just going home anyway. But and they did, and initially they had such low SID because they were lazy. Then really just going back to do it again doesn't really make any sense. But that's certainly a rationale for cutting the anatomy. And when now in our digital world, all this stuff, if that person's name is associated with the image, those repeats that you say don't send are still logged, right? We even have that here. You notice like it just puts a little X on it. It doesn't like disappear. I mean, maybe eventually when we use up the memory, but I think since we've had this thing, we haven't had to like delete an image to make room. So I don't know what was going on there. Try not to follow that example for your own good. And I can guarantee that they used the same technique that they would have used at 40 or more, which means the patient got even more exposure too. We'll have to talk offline. Okay, variables affecting subject contrast. We've kind of switched gears and we don't have a whole lot of time. So even if we don't finish, I'll do this video again. And we'll see. So what do we have here? KV versus contrast. So it's minimal now, right? We need enough KV to penetrate the part. That part is true. Does scatter go up when KV goes up? That's true, although most of the scatter is coming from the patient. So technically when KV goes up, contrast goes down because there's a little bit more scatter, but no longer as relevant because of digital technologies that fix things for us. Problem, as we mentioned earlier, is if you don't have enough KV. And generally speaking, we want our KV to be higher because we need to penetrate the parts. You shouldn't be lowering your KV to try to increase the contrast. While that's technically true, again, it wouldn't make that much difference because digital world will fix things, and then digital world doesn't fix KV that's too low anyway, if it's way too low. So, the best example for this slide is to talk about the KV going up versus the KV going down. Right. Question? Yes.
So this always increased KV is better.
So the rule will always increase KV. I don't know. I can tell you that from analog to digital imaging, right, when we were using film, the techniques now are about 10 to 15 kV higher across the board for every exam. Right. The rationale is a couple of things, right? Like we said, digital imaging systems work better with higher exposure, and higher kV leads to higher exposure. And And also you ensure that you're penetrating the part. And third, you can lower the dose if you have an associated reduction in mass, right? So if the kV goes up and you lower the dose significantly by lowering your MAS. If they both go up, then you're not lowering any exposure, right? Generator, again, in terms of contrast, and the reason why, I mean, if you understand the last slide and you think about generator as giving you more kV, like a higher percentage of photons are going to have a higher kV when you go to a more efficient generator, that's essentially the same as saying, I'm starting with a higher kV. And what does kV do to contrast? So a higher kV is going to reduce contrast. Thus, in a way, a more efficient generator could lead to a small reduction in contrast. But digital imaging is really good at fixing contrast, right? Provided that you have at least enough kV. Do you guys understand? When you're working with generator questions, you really need to ask yourself, is my kV overall, right? So it's kind of like a bucket of water that with an inefficient generator is going to have a lot of different kVs and not so many at the actual kV level that you set. Go to a more efficient generator, pretend it's a bucket of water, right? The photons in there are going to be more likely to actually be the kV that you've set. No longer relevant. My whole course is becoming less relevant. At least for kV. But wait and see. I'll be very happy soon because we're going to get all into all sorts of digital stuff soon. Yeah. Yeah, all the fun stuff is happening soon. So, filtration. So is filtration going to have an effect? No, not really. Right? Assuming, so it is an assumption, right? And at some point you have to say what would happen if one photon that was kind of on the longer side slipped through. Right? You can't really make, so the assumption is that the longer wavelengths don't make it through. Those are the photons that have lower energies, lower kVs, if you want to think about it that way. But since they're not affecting the image receptor again, then they should not have an effect on the contrast of the image. As a thought experiment, every once in a while, I'll say to myself, well, what if you did this and there was no patient there, right? And all you were doing was exposing the image receptor. Then there might be a change. But how often do we take x-rays on no one? Right? So it's a thought experiment that really wouldn't happen. It's just a theoretical kind of thing, right? I mean, unless you're doing some type of quality control, but yes.
So you're saying that the effective filtration doesn't affect it, but the compensating?
Compensating, yeah. Right? Yeah, so again, there's a distinction, thanks. I'm like, sometimes I just look at my slide and not read everything that's there. There's a distinction between a compensating filter, right? Remember, the filter that's in the tube only affects the primary beam. The compensating filter is designed to allow portions of the radiation to go through, more where you need it, less where the object and thickness is lower, where you don't need it. And that in turn is designed to affect the contrast and make the contrast more uniform over the entire object. So compensating filters very much so directly affect the contrast of the image. That's what they're for, right? Or else one side would be much darker than you wanted it to be, and the other side might be much lighter than you wanted it to be. It's the whole reason we use compensating filters.
We haven't seen one before, have we?
No, only I don't think we have any. I know. don't lose too much sleep over it. But is it already that time?
Yeah.
So hold on, before we get going, let's see where we left off so you guys can remember. So we're about at 20 here. 19. Yeah. So we will continue this conversation, and you can watch this video and hopefully the rest of it. I think the digital components of this that take more of our thinking, we'll be talking about in the lab, where we can take our time and not have me speak 100 miles a minute.